In this module, we'll compare centralized, federated, and decentralized identity models. You'll see how each approach distributes trust, control, and data sharing, and what that means for designing compliant, scalable eKYC and AML architectures in real-world environments. Choosing an identity model is really about deciding how control, data, and liability are distributed. Control asks, who actually authenticates the user and makes binding statements about them? Data asks, where is PII stored, who can query it, and how widely is it replicated? Liability asks, when something goes wrong, who regulators and auditors will hold accountable for those identity decisions? Centralized identity is the classic IAM model. One system owns the account, stores the attributes, authenticates the user, and makes access decisions. The upside is strong control and relatively simple governance. You know exactly where identity lives, and you can enforce policy consistently. The trade-offs are significant. That central store becomes a single point of failure and a high-value target. Identities are siloed, so users can't easily reuse verified identity across organizations. The result is repetitive KYC checks, fragmented risk views, and higher onboarding friction. Federated identity pushes trust out to a dedicated provider. Instead of every application managing its own credentials and lightweight KYC, an identity provider handles authentication, identity proofing, and token issuance. Applications, relying parties, agree to accept those tokens under a trust framework. They focus on local policy and risk controls, like step-up authentication for high-value actions. This reduces password sprawl and duplicated onboarding. But it also concentrates risk. If the IP is compromised or misconfigured, every connected relying party is exposed. Traditional eKYC models force each institution to repeat essentially the same checks. Users experience friction, onboarding costs go up, and results vary from one institution to another. All that duplicated data tends to land in large centralized stores, architectural breach magnets that may sit in awkward jurisdictions, making data residency and sovereignty hard to guarantee. Users also lose visibility and control. Once data is sent, it's copied and reshared in opaque ways. And these systems are optimized to authenticate a session, not to produce portable regulator-grade proof that another institution can safely rely on. Decentralized identity flips this pattern. Instead of one big provider holding everyone's identifiers and credentials, a distributed network anchors trust, but not PII. Each user has a globally unique DID and cryptographic keys they fully control. Those keys prove control of the DID and sign verifiable credentials, while the raw personal data lives at the edge with the user or their chosen wallet. For architects, this removes the central honeypot, reduces the blast radius of breaches, and enables cross-platform interoperability without centralizing identity data. Verifiable credentials use a simple triangle of trust. An issuer, such as a bank or government, runs its KYC and signs a credential describing what it verified. That signed object is the core evidence. The user, as holder, stores this credential in a wallet under their control, not the issuer's. When another institution needs KYC, it acts as verifier. Instead of pulling raw data from the issuer, it asks the holder to present a cryptographic proof, which can be scoped, minimized, and checked for tampering. Zero-knowledge style proofs let us answer yes, no questions about identity data without revealing the data itself. Rather than sharing a full document with name, date of birth, and ID number, the user produces a cryptographic proof of a statement like this person is over 18 or this document passed KYC checks. The verifier checks the proof, not the raw attributes. Architecturally, this enables strong data minimization, reduces PII sprawl across services and vendors, and significantly limits liability if a verifier's systems are later breached. Trust registries are the bridge between cryptography and regulation. In a decentralized ecosystem, anyone can technically issue a credential. Verifiers will only rely on it if a governed registry says, these issuers meet our rules. You can think of the registry as a curated list of acceptable issuers, backed by an eIDAS scheme or an industry consortium. Your verifier first checks signatures for mathematical validity, then checks the registry for governance validity. That two-step check is what makes decentralized KYC credentials usable in AML-regulated environments. Selecting an eKYC architecture means trading off where complexity lives and who carries privacy risk. Centralized models are simple to operate and highly auditable, but they're poor at data minimization and portability. They create strong UX lock-in and large, attractive honeypots for attackers. Federated identity improves user experience and sharing of KYC, but you inherit ecosystem governance issues and cross-domain failure modes. Decentralized models with verifiable credentials invert the trade-off. You gain strong minimization and portability, but you take on higher ecosystem complexity, new trust registries, and more demanding client implementations. Centralized and federated models give regulators a single institutional log. That means straightforward traceability, clear liability, and high comfort, even if the model isn't very privacy-friendly. Decentralized and SSI models distribute events across wallets, registries, and off-chain logs. You gain user control and portability, but you must deliberately design how those events can be reconstructed and proven later. The goal is not to choose one side. Architect for absolute traceability, then incrementally layer SSI on top of traditional logs, so every KYC decision remains defensible in an investigation. You can think of modern identity, KYC, and AML as a three-layer system you compose. At the core, keep what regulators and auditors care about most. Centralized, strongly governed systems for ledgers, immutable logs, and jurisdiction-specific compliance. Above that, the access layer handles federation and SSOs, expressing trust inside your ecosystem while hiding internal complexity from clients. At the edge, use decentralized verifiable credentials, so customers can reuse KYC, share fewer raw attributes, and still pass checks. Your real design job is to tune the boundaries between these layers to match your risk appetite, ecosystem maturity, and regulatory context.